In this video, we're going to talk about minimum spanning trees. Minimum spanning trees. So first of all, we should define a spanning tree. A spanning tree for a graph they call the graph G, is a subgraph of G that contains every vertex of G and is a tree. And so that's the definition of a spanning tree. And a weighted tree, a weighted graph is a graph for which each edge has an associated positive number or the real number weight. So again, a weighted graph of course has vertices, edges, but the edges are each assigned a number. Those numbers could represent miles, they could represent costs, they could represent feet. And the minimum spanning tree for connected weighted graph is a spanning tree that has the least possible total weight compared to all other spanning trees of the graph. So those are definitions. So we have a spanning tree. Again, a spanning tree contains every vertex and it is a tree. So basically what it implies is you can get to every vertex by going along the edges somewhere, because it is a spanning tree. It covers every vertex and the tree. And a weighted graph is a graph in which those edges are assigned numbers. Like I said, they could be weights or dollars, or they could be lengths, anything like that. And then the minimum spanning tree is a spanning tree, and this is what we're going to mainly be focusing on, or minimum spanning trees. It's going to be a, uh, a weighted graph is a spanning tree that has the least possible weights compared to all other spanning trees of the graph. So that's what we're going to be focusing on. And so we're going to try to find these minimum spanning trees. And there's a couple of algorithms we're going to use. So it's a method to find minimum spanning trees. And one that we're going to consider is called Kresgel's algorithm. And so with this method, you can construct a spanning tree by doing the following. Begin with the smallest weight edge. And add that edge and the two vertices connected to it. To again start with the smallest weight edge, add that edge and the two vertices connected to it. Then add the next smallest edge. And the vertices that it's connected to. Of course, obviously, if one of the vertices is already there, you don't have to add it. We do have to add the edge and continue by adding the next smallest. So to continue doing that, you go to the next smallest. In this way, unless adding that edge will cause a circuit in your graph. So continue this way, and unless let me fix that wording a little bit. Unless adding that edge will cause a circuit in your graph. So continue to do that, continue to add them on, and continue until you've considered all edges. So that's Kreskov's algorithm. So let's do an example. And let's do this example here. We have this graph. And again, this graph could represent, maybe this could be an airline, and this could represent hundreds of miles. So maybe 500 miles between city E and city D, 100 miles between city D and city C, etc. So these numbers could represent, say, hundreds of miles, or these could be pipelines between cities. And again, numbers could represent the miles of pipeline that's required between the cities. And there are many different applications for this. So what we want to do, we want to turn this into a graph that's a spanning tree. In other words, so that all the vertices are connected, but that this total weight of the numbers in a spanning tree is low as possible, as small as possible. So let's take a look at that. So you can stop the video for a second if you want to copy this graph. And so again, we're going to find the minimum spanning tree using Kreskov's. And so there's several ways to do this. We'll maybe write down the vertices without the edges. And so there's the vertices A, B, C, D, E, F, G without the edges connected. And so let's make a little table. Again, we're going to use Cresco's. And so again, over here, we're going to put the steps. And here we're going to say whether or not we added that edge. And then put the weight over here. Again, if we look at our graph, let me pull this up a little bit so we can put everything in the same picture here. Let me refocus this. So let's start is according to our algorithm, we start with the smallest weighted edge. And that's going to be this one DC. And so we're going to put that DC on over here and put that one with it. And then, yes, we added it and put the weight down, which was 1. So we started with the smallest edge, smallest weighted edge, and put that edge in our new graph and wrote down the vertices it was connected to. And yes, we did add it and then put the weight of it down. So now go to the next one. Go to the next smallest weight is 3 on our graph here. So let's put that one in. That was, you can call that AC or CA, it doesn't really matter. We call that CA. Again, it doesn't really matter what you call these. You can call them this AC or CA. Same with the first one, we could have called that CD or DC. And so we put its weight, we added that one on. And now 5 is the next smallest one. Again, remember, we will add these on unless it causes a circuit to appear. So this was DE or ED. That was a 5. Next, let's see, what's the next biggest one? It looks like the 7 is the next one. And that's over here. Again, we're still not, none of these have caused a circuit, so that's why we keep adding on. I'm going to call that BC or CB. That was a 7. And the next smallest one is going to be an 8. And that was CG. For GC. And let's go to the next smallest one. It looks like a 10, huh? This is AB is 10. But look, this time, if we were to add a 10 here, if we were to put this edge right here, this would cause a circuit right here, wouldn't it? So we cannot add that one. So anytime if you would put an edge in, and it would cause a circuit, don't add that. But mark it on your graph here, AB, and just put a no here. No, we didn't add it. And don't put the number down. So that was 10. And what's the next largest one? It looks like 13. 13 is the next largest one. And that was BF. And we can add that one in. Because that's not going to cause a circuit. So BF. And we'll go yes. What was that? 13. Now let's check what's the next one. It's going to be AF. But if we do AF here, notice that's going to cause a circuit. So that one's going to be no. And so that was 15. We didn't add that. So what's the next one? Is it looks like 19 is the next smallest one. But if we put that one in here, notice that would cause a circuit. So we're not going to add what that? Yes, give me BG. Yeah, BG. If we would put BG in, which was at 19, it would cause a circuit. So no. Uh, then let's see, what's the next smallest one? Looks like 22 is next smallest one. That would be GF. But notice if we put GF in, that will cause a circuit. And then finally, EA is the last one. But notice if you put EA in here, it'll cause a circuit. Right there. So this is our minimum spanning tree right here. That's the minimum spanning tree. And then the total weight would be these numbers of the edges that we did add. And total weight, if we add these up, let's see, this is going to be 4 plus 5 is 9, 16, 24, and then 37. So again, when you're using Kruskal's algorithm, it's very important, again, to show these steps here and say, you know, whether you or not you've added the edge. Now there's another algorithm. And it's called Prim's algorithm. Again, this is for a minimum spanning tree. This will give you a minimum spanning tree just like Kruskal's did. So now this method is begin with any vertex. Remember in Kruskal's, we began with the smallest weighted edge. With this one, you begin with any vertex at all. Step 2, add the edge. Of the smallest weight. that is connected to your original vertex. So far we have that you pick any vertex, then add the weight, the edge, the smallest weight that is connected to that original vertex. And of course along with that edges, other vertex. Then at each step, consider all the vertices you have so far. Then add the lowest weight edge. That is connected to any of those vertices. Unless it creates a circuit. And then continue in this way until you're done. Continue until you'd stop when you have a spanning tree or have considered all edges. So you sort of something like that. Again, the finishing, even on the last one, we actually could have finished, even when we did crestals, we could have stopped right when we saw that we had a spanning tree. And so that's an option that you have available. So again, let's go back to our same graph that we did for the last example for crestals. And now this time we're going to use Prim's algorithm to find the minimum spanning tree for this graph. And so let's do this again. We're going to take a look at Prim's. Once again, it's usually helpful maybe to put down all the vertices. this. And now again, you can start wherever you want. It doesn't really matter. Let's again, you can pick any one, a hard one. Let's begin with B. Start with B. So start with B, and again, let me mark those before I said steps. So again, since we're starting with B, then you look at B and see what the smallest weight that's connected to B, and it looks like 7, and that's BC. Yes, we'll add that one, and the weight on that one is 7. And then so now when we add this in, we add our 7 in. Now we look to see, so now we have 2 vertices involved, B and C. So now we look to see what the smallest weight, the next smallest weight is connected to any of these vertices. So just look, so we're only going to consider things connected to B and things connected to C. And actually, the smallest weight edge that's connected to either one of them is this 1, obviously. So we're going to put that in. Again, we only considered the ones that are connected to B and C. And so we're going to put that one in, which was CD. And yes, we added it. That had a weight of 1. Now, again, we're going to consider now just the vertices we have, which are B, C, and D. So what's the smallest weight edge that's connected to B, C, or D? And B, as you look up here, it has a 10. C, actually, C has a 3, doesn't it? And then D has a 5. So it looks like this one right here is the smallest weight one that's connected to any of the vertices we had so far. And what is that? AC, CA, or AC, whatever you want to call it. You can go either one. And that was a 3. So once again, consider A, B, C, and D. And what's the smallest weighted edge connected to any of those? And it looks like this 5 would be the one. And that was ED or DE, whatever you want to call it. And that was yes. And that was a 5. So let's keep going. Consider these vertices we have. A, B, C, D, E. It just was a coincidence that happened to come A, B, C, D, E. It won't always be that in order like that. But in any case, look at the next smallest one that's connected. It looks like this 8, huh? The smallest edge that's connected to any of the A, B, C, D, E is going to be this 8 here. And we can call that CG or GC. Now we're going to consider the smallest weight that's connected to A, B, C, G, D, or E. And looks like that's going to be this 10, huh? This 10 up here between A and B is going to be the smallest. But again, we don't want to have a circuit, but we added that. That'll make a circuit. So this is A, B, and that's going to be a no. So now what's the smallest one that's connected to A, B, C, D, E, or G? It looks like it's going to be this 13, huh? That's going to be the smallest one connected to any of those vertices. And yes, we're going to add that because that's not going to cause a circuit. 13. Now notice we have a spanning graph. Or excuse me, a spanning tree. We have a spanning tree here. So we could stop right now. And so we could stop right at this point. Though if you want to go through the process just to be sure, you can go through and check all the others, what's going to be the next one connected to any of these. It looks like it's going to be the smallest one, AF. But again, you see that's going to make a circuit. And then what's the next one after that? Looks like BG would be the next one, but see, that would make a circuit. Then what would be the next one? Looks like FG, but you see FG would make a circuit. Then finally AE or EA, if we put that in, that would make a circuit. So like I say, we really didn't need to do this because we had a spanning tree. Remember, it's a graph that in which all the vertices are connected, and of course it's a tree. And so once again, let's find the weight 7. That's 8 plus 3 is 11. 5 is 16. 24, 37. So it's the same that we got for Kruskall's algorithm. And in fact, we got the exact same graph. If you look back at Kruskall's, which was here, the graph was exactly the same. So Prim or Kruskall's will give you the same minimum spanning tree with the same weight. And it's good to know how to do either algorithm. Now let's consider this example. This is a little bit different in that, again, everything's very similar, except we have duplicate weights. So whenever you have duplicate weights, you're going to have two different graphs. So the duplicate weight, so we're gonna have one graph, we pick one weight, another graph, we pick another weight. So let's just go through that process. Again, we'll use Kruskal's. So again, just like before, put down all the vertices, and then make a little table. Always make a table here, put the steps, and whether you added it or not. And the weight. So again, let's go through this. And again, remember for the Kruskal's, we start with the smallest. Let's look at our graph here. Start with the smallest one, AD. And yes, we'll add that. And that had a weight of 1. Then go to the next one. Looks like it's DC. Remember, with Kruskal's, we just look at, do them in order. Next one is this one. And the next one, now here we can choose, we can either add this 5 or this 5 first. So let's add this 5. And next one, let's add this 5. Now, if it ends up that you can add both of the duplicates in, then it doesn't really matter what order you did them in. So in this case, notice that it turns out we added them both in. So it really would not have mattered which order you picked those. So we could have put this one ahead of this one, or this one ahead of this one, didn't really matter. So, and then so let's go to the next one. Looks like the next one's 7. And now the next one would be this 8 here. But if we put this in, that'll cause a circuit. So we're not going to put that in. And the next one here would be 9. So we're not going to put that in because, see, that would cause a circuit here. And the next one would be 10. We're not going to put that one in because that would cause a circuit. And let's see, what would the next one be? It looks like the next one would be 14. That one we can put in, huh? And now we could actually stop here because you see we have a spanning tree. But just to be sure, let's just check the last couple of ones. FG, if we put FG in, that would make a circuit, so that one would be a no. And finally, AB, if we put that one in to make a circuit, that's gonna be a no. And so let's do the total weight. Let's see, we have 10, 20, 21, and 14, is that 35? That. So now, again, we picked, remember we had these duplicates, we picked excuse me, we picked DE first and then picked BD second. But since they were both added, then it really wouldn't matter which order we did it. So, like, for example, if we would have picked DB first, then we still could have added DE. So again, if you have duplicates and all the duplicates end up being a yes, then it doesn't matter what order you pick them in. So you only have this one minimum spanning tree. So this is the minimum spanning tree. Let's do another example, and we'll see if in this example, if order makes a difference. So again, we're going to use Kruskal's. A, B, E, E, E. It's that left off letter, then this one I should have had an F back. Please add this F over here in the example. F and G. So again, let's look at this example here. Once again, put down your vertices. And let's go through the normal steps. And let's do it. So once again, start with the smallest value. And the smallest edge, it looks like this 2. We added that on. Then go to the next smallest. It looks like that's this 3. And go to the next smallest, which looks like that's this 4. And now here again, we have a choice. We have 2 5s. That's going to be the next smallest, one of these 5s. So let's pick one of them. Again, let's pick AD. But now notice this time when we picked AD first, we cannot add DB. So because notice if we add a DB, we would make a circuit. So this time it's going to make a difference which order that we did these in. So we picked, so let me just put like a star over here to show this is where we made our decision. We picked AD rather than DB. And then once we picked that AD, that closed this loop here. And so it would have made a circuit if we'd have did BD or DB. So let's continue on. What's the next smallest? It looks like it's this 7. Notice we cannot add the 7. BE is no. And we cannot add, yes, we can add the 8 though, huh? Over here we can add this 8. CG. Yes. And let's see what is next. It looks like it's this 10, but notice we cannot add the 10 here, huh? We cannot add the 10 because we'll make circuit. And what's the next one? Looks like the next one is an 11. We cannot add that because that'll make a circuit. And so what is next? It looks like the next one is this 14. We can add that one on. And then finally, the highest one is 15. But if we added that on, we would get a circuit. So let's just, I'm going to just count all the original edges, be sure we've covered them all. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. 2, 4, 6, 8, 10, 11. Looks like we've considered them all. Then add the weights up. And we're going to have, what's this, 5, 9, 14, 22, looks like 36. So let me just double check my numbers here. Let me put, let's see, there's going to be 10 here, 24, 27. Looks like this is correct. So again, the key though, in this time, we pick this AD rather than BD. And when we picked the AD, that made it so we could not add the BD. So this time it's going to make a difference. So let's do the other options, go through the same steps, except when we get to this point here, we're going to choose the other options. Let's go through that. And once again, vertices here. So those are our vertices, A, B, C, D, E, F, G. So once again, we go through the same steps using, again, we're using frescoes. And just like before, look at your graph. I'm going to start with AD. Yes, we're going to add that. It's going to give us a weight of 2. So we're going to add BC. B was 2. BC was 3. And that's kind of messy there. And then we're going to add AE. That's the next one from our graph here. 4. And now again, so the last time at this point, when we had a choice between AD and DB, which reached 5, we picked AD. So this time we're going to pick BD. So we're going to put that one in. So let me put a star there. The fact that we picked, let me just clean this up just a little bit here. Just a little bit neater. So this time we picked BD rather than AD. And so just put a star just reminds us that now therefore now we can't add AD because we make this circuit. So for AD, we have to say no this time. And then what's the next one? It looks like it's going to be DE. But this time we cannot add DE, can we? Because that'll make a circuit. And then what is the next one? Looks like CG. CG was 8. And that was an 8. And then what's the next one? Looks like BC is next, but notice that'll cause a circuit. Next one looks like it's going to be EG. EG here. So actually, that's a no, because that'll make a circuit. Next one is EF. That one we can add. And then finally, FG is going to be a no. That'll cause a circuit. Well, actually, I should have put the number for EF right here. This should have been 14. And let's see, 10, 24, 33. Looks like this is 36 again. So the total weight equals 36. Now, in those cases, so it's the same total weight as the last one. In those cases where you have a choice, it's not always going to be that the weights are going to be the same. Now you do notice the graph is slightly different. So here's the graph when we pick AD. And here's the graph when we picked DB. So those are slightly different. So the spanning trees are slightly different. Though it happened to be the weights are the same. Though, like I said, it's not always going to be the case where the weights are the same. So this problem, there was some slight difference when you picked one or the other. So always keep that in mind, that when you have the options, when you have like options like this, where you have edges that have the same weights, you could possibly have two different graphs. Now, as I said, but from the previous problem, we found that if you end up adding both of them in, then it doesn't make any difference. But in this case here, when we did AD first, it made it so we could not add DB. And then we did BD first, we could not add AD. So this time it did make a slight difference. And so keep this in mind whenever you have duplicate edges, duplicate weighted edges, whether you're doing press golds or prims, you have to consider all the cases.